Hello, let's do the monad navitry exercise. So here we've already established that list is a functor whose underlying map on objects is given by the list transformer, and it's using list map as the map on morphisms. And now we are asked to prove that it's not only a functor but also a monad. And we'll be given this little hint up here, as we'll probably get back to at some point. So the first thing we have to decide here is what is the underlying functor, and that's obviously going to be the one we just had there. Then we need a return, so this is the thing that takes a pure thing and gives us a list of those things. So it's a natural transformation, which means that we have to transform something. So that says for every set x, we have to go from x to list of x. So if I have a given x, then here I have to make a list. And I can only really think of one way to do this, which is to make a singleton list, right? Or to be precise, I can think of many ways to do this. I can make 2 copies of x or 3 copies of x, but the only thing that feels natural in an intuitive sense is to just use x once, right? Because it would be quite strange to use it twice or 17 times. So I think that's the right one. And we're going to see if it's the right one if we can prove the equations for it, right? So the first thing we need is that this is natural, meaning that it doesn't matter if we map before or after we make the singleton list. So if we get a function from x to y, then what we need here is that these two functions should be the same, but they are obviously the same. So that was easy, as it usually is. The join, on the other hand, is something that's supposed to go from list composed with list to list. So that says that you should be able to take a list of lists and just give back a single list. So how can we do that? Well, we have to say how to transform. So that means for every x, we should be able to do this. And if you think about it, if we have a list of lists, then we can concatenate them all together, right? That's probably why we've been given this little hint up here. So if we just concat, that is doing exactly what we want. Then we have to see if this is natural or not. So that means that if we have 2 sets x and y, function between them, in general 2 objects and a morphism between them, we're in set, right? Then we need these 2 functions to be equal, which, okay, it looks even worse if we haven't fully normalized away the category stuff, but we're in set, so that means that composition is just function composition, etc. So we need these 2 functions to be equal. So we're going to use function extensionality for that, which means that they only have to be equal for every argument x. Okay, so I think I need to pattern match an x in order to do this. So I'm going to make myself a little helper function, which is going to have exactly this type. Okay, but I can't resist calling this XSS because it's a list of lists. What else? I know that this is actually the definition of concat, so it's going to be a bit clearer if I write that out. Okay, so I think that's what I need. Then if I changed x to XSS in one place, I have to do it everywhere. Okay, let's check that the lemma fits. It does. Okay, and then this I'm going to do by pattern matching on axis. This. This looks easy. And here. What can I do? Well, I could do a recursive call and see what happens. Okay, and this looks like, on the one hand I have a list map applied to an append, and on the other hand I have a list map outside the append. I think I need some kind of corresponding fact here. Map deals with appends. So if I have 2 sets, function, then if I list map with f over list x's, so I need these as well. Then I append with list.map fy's. I think that should be the same thing as just mapping over x's append y's. I think that's what I need. And my x's is x's and my y's is concat x's, I think. Yes. Okay, so then here I get an f, x's and y's. Because I know that append is pattern matching on its first argument, and list map is pattern matching on x's, then clearly I should also pattern match on x's. Okay, I'm not sure what happened there. Yes, the mistype. Okay, that looks like refill. And here the first bit looks good, so I need to con that away. Then I have to deal with the rest of it, but that looks like a recursive call. That's good. Okay, so that shows that this concat thing is actually a natural. But now I also need to show that it interacts with the return in the appropriate way. So the first thing we need is that these two functions are equal. Okay, so again, I guess I could just do this in a lemma, or I can go and find it in the library probably. This is what I need. Wait. Okay. I think we have done this many times before. Let's just see that that's what I need. And we do it by pattern matching on x's. This case is easy. And this case is a Kong x. Right. So that's second nature to us by now. What about this one? Well, again, two functions are equal. Use extensionality and then prove it in a lemma. What do I need? This. Okay, but I know that this is actually concat. And I know this is how I define my return. I guess I just keep it like this. Okay, what do I need? That's what I want. Okay, so in this case, that's easy. In this case, the first thing is good. Now it's recursive call, so that's more of the same basically. And what about this one? Well, again, it's two functions being equal, so I better make this into a lemma. Okay, and this is what I need. So I can simplify this a little bit. So first of all, this is a triple list, a list of lists. And well, I know that this is definition of concat. Okay, this is the definition of concat. And this is concat, right? So I can either concat twice, or I can first map concat and then concat once more. That should be the same. Okay, let's see what x is. Let's check that the lemma fits. Yes, it does. Okay, and we pattern match on the only list we have. In the base case, it is easy as expected. In this case, let's see what we have. So it's a little bit hard to see, but we remember that this is concat, right? And then we see here we have a concat of an append this time. So this is the function given to the fold as part of the definition of concat, but this is really an append. So that's exactly what this little thing is talking about, right? So I think we should try and rewrite about that function. And what's our left hand thing? It's XSS, and our right hand thing is concat of 3 of these. Okay. So what happened? Now it's looking better. So all of this is the same. Actually, all of it up to here, right? But this is still different from that. But actually, this is exactly what the left-hand side of a recursive call is. And this is what the right-hand side of a recursive call is. So I've trained myself to recognize this concat as fold right of append and nil. So I think if I also do a recursive call here, then this is actually going to be just refl left. Okay, so that's good. And then the only thing we have to do is we have to prove this thing. So let's see, how would we do that? Well, this is pattern matching on the left hand thing, so let's do the same. Okay, that one is easy, as it usually is. And for this one, what do we have? Okay, so we basically have the right start, but it's bracketed differently, right? So let's see if we can find something that re-brackets. That's going to be something like plus a sock, right? If we do plus a sock of, did we have excess and concat excesses and concat y's, then the sum of that then that matches the right hand side, right? So actually, I don't think we want to sim. I think we just want to rewrite like this. Okay, and then we see that the first thing here is good, and the rest of it we can do with just a recursive call, I think. Yeah, so that's now looking good. Right, so proving this fact wasn't so hard. It's just the fact that we needed to see that we wanted it down here. So what have we done? We have said that the list functor is actually a monad by using singleton list as the return and concatenation as the join. and then proven that all of the expected equations actually hold.